As I believe I mentioned at the end of our last class meeting, today will be our introduction to three-phase circuits. So in most industrialized countries, electrical distribution from utilities to consumers is accomplished using a three-phase distribution system. Up to this point in this class, most of the circuits that we have analyzed would be considered a single-phase circuit. So a single-phase circuit can be broken down like so. So we might have some terminal A, a voltage source, some terminal N here, and I'm going to call this voltage source VP angle theta V volts. Here will be terminal capital A. Here will be ZL. Terminal capital N. Like so. So a couple of things that I'd like to point out here. So this is effectively just a Thevenin equivalent circuit representation of really any circuit that we've been able to deal with, where the practical source is formed by that voltage source located between terminals A and terminals N, and then the resistance or impedance of that practical source is represented by the transmission line impedance, ZW. So in a system like this, we have what's called a hot wire. So that would be the connection, the transmission line between lowercase a and capital A. And then down here on the bottom, we have what's called a neutral wire between lowercase n and capital N. And I can segregate or separate this system into three distinct parts. On the left-hand side, we have our source. In the middle, as I mentioned previously, we have our transmission lines. And then on the right-hand side, we have our load. And again, this is nothing more than effectively a Thevenin equivalent circuit for any steady-state sinusoidal system that we've looked at to this point. Well, a three-phase, three-wire system is going to look similar, but there's going to be some key differences. So let's say that I have A here, B here, terminal C here. So this would be our source connection. I don't know if you can see that, so let me redraw it, but that's supposed to say ZWA, the impedance of the transmission line for the A phase. ZWB. ZWC. And then on the right-hand side, we will again have our load. ZLA, ZLB, ZLC. And I'm going to label a couple of things here like I did on the last one. So this line would be the A phase line or wire. Then we have our B phase line and our C phase line. Everything to the left of the lowercase letters is our source side of things. Everything to the right of the uppercase terminals is our load side of things. And then everything in the middle is again transmission lines. All right. So in this system, which is called a three-phase, three-wire system, or you may see it as 3Phi 3W on technical documents. We can actually submit 3 times as much power as the single phase system that I've drawn above, using only 1.5 times the number of wires. Excuse me. And so we can see that from a distribution perspective, being able to transmit more power using less wires is a very cost-effective approach, which is why three-phase power distribution is used in pretty much every aspect of the industrialized world. Additionally, three-phase systems produce a rotating magnetic field with a specified direction and constant magnitude, which means that any electrical motor that is connected to a three-phase system will actually experience the smallest magnitude of vibrations. If everything is perfectly balanced, which we'll talk about in great detail on Thursday, the motor should experience exactly no vibrations because it has a constant applied average power. So with regards to the transmission lines and the loads here, these are all simply impedances. We characterize them by their impedance, which is something that we have pretty thoroughly covered in the steady state sinusoidal portion of the class. So for right now, the only thing that's really truly new is this concept of three-phase voltage generation represented by the source section of the circuit on the left. I'm going to attempt to draw a picture, and I'm going to tell you now that it is going to be terrible, but I think you'll be able to understand what I am drawing. So all right, so these two concentric circles that I've drawn represent what's called the stator of a rotating electric machine. And what I'm doing right now is drawing these little boxes, which will be terminals. So I'm going to say that this guy here corresponds to the A phase, and then this one subsequently 180 degrees across the circle from it is representative of what I'm going to call A prime. 120 degrees away from A, I have the B terminal, and then 180 degrees across from that, I'll have B prime. And 120 degrees away from the B terminal, I have the C terminal, and 180 degrees across from that, I have the C prime terminal, okay? The A terminal usually has a black wire, and I say usually in America, it has a black wire. In Europe, they use a different color convention. The B phase is typically denoted by blue wiring, and the C phase is typically denoted by red. And then all of our prime phase terminals are going to be in gray, like so. Now I am just simply trying to draw a wire out to a terminal that we could access outside of our rotating electric machine, which in this case is trying to represent a generator. Actually, I'm going to draw these in gray so that I don't have so much stuff overlapping. Here's B. Here's C. And here is terminal N. So inside our stator is what's called the rotor. And it is a magnet. And this is a very simplified explanation of what's going on. And this magnet is allowed to rotate with some particular angular frequency, omega. And so for those of you that have had Physics 202, which I hope is all of you at this point, should understand that when this magnet rotates, the magnetic flux seen by terminal A will change as the magnet spins, right? So when it's in alignment, like we have right now, with the North Pole aligned with terminal A and the South Pole aligned with terminal A prime, terminal A sees the maximum amount of electromagnetic flux, and due to Faraday's law of induction, this causes a peak value in the voltage. So between here and here, we'll have some induced voltage, VAN, as a function of time. And now I'm going to try to draw what's going on with these voltages, and I'm going to apologize for how crappy this looks as well. So here is time. This is voltage. And so the A phase is going to look something like this. We have some maximum magnitude. Like so, where VAN of t will be equal to VPA cosine omega t. As the magnet spins in its counterclockwise, spins counterclockwise along that axis of rotation, after exactly 120 degrees of rotation, the flux through the B phase of the rotor, the stator, will be at its maximum value. And so voltage will be induced between the B phase and the neutral, VBN of t. And since I'm using blue, so that's 90, so this will be about 120. Where we have VBN of t will be VPB cosine omega t minus 120 degrees volts. And after, excuse me, after another 120 degrees of rotation, we should see that the flux is maximum through the C phase, inducing a voltage VCN of t. Which is going to look something like this. VCN is equal to VPC cosine omega t minus 240 degrees. Some textbooks and explanations would consider this to be VPC cosine omega t plus 120 degrees. But I prefer to look at things as the B phase is lagging the A phase by 120 degrees, and the C phase is lagging the B phase by 120 degrees. There's nothing wrong with saying C leads A, which leads B, but I prefer the perspective of A being our effectively reference voltage, and then measuring the B phase and the C phase with phase A as the reference, okay? So the reason why there is exactly 120 degrees of phase separation between the A phase, the B phase, and the C phase is because those terminals are physically located 120 degrees away from each other around that circle, okay? So the only way to cause an imbalance in the phase angles for this three-phase voltage generation source is if it is physically constructed poorly, such that there isn't 120 degrees. So to be clear here, I'm saying, attempting to say that this angle is 120 degrees, this angle is 120 degrees, and this angle is 120 degrees. And that's what generates these differences in phase angles for our three different voltages. Now, if the coils that are sensing the change in magnetic flux, so the coil that leads to terminal A, the coil that leads to terminal B, and the coil that leads to terminal C, are all identical in shape and in the number of turns or windings, then the magnitude of each phase voltage will also be identical. So under that condition, let me write that explicitly. Then we would see VPA will be exactly equal to VPB will be exactly equal to VPC. So effectively, the magnitudes of all of the voltages are identical. If this condition is met and theta B is equal to theta A minus 120 degrees, and theta C is equal to theta A minus 240 degrees, we have what's called a balanced three-phase generator, or a balanced three-phase voltage source, okay? We are going to be looking at all of the systems in this class will utilize a balanced three-phase generator or balanced three-phase voltage source, because the only way to imbalance a three-phase generator is to construct it incorrectly, which does not happen. We might observe that there is a slight difference of maybe a couple of millivolts or maybe fractions of degrees due to manufacturing tolerance errors, but it's never going to be enough to cause actual imbalance in the system, which is what we're going to talk about towards the end of things here. Okay. So we can actually get two different sets of voltages from a balanced three-phase generator, depending on the direction of the rotation of the rotor. These are called phase sequences. So for a positive or ABC phase sequence, the RMS phasor voltage across the A phase of the load, VAN, will be given by VP angle 0 degrees, where in this case VP represents the RMS magnitude of our sinusoidal wave. VBN will be VP angle negative 120 degrees, and VCN will be VP angle negative 240 degrees. So that's just the RMS phasor domain representation of those three time domain voltages I drew out earlier. If our rotor is rotating in the opposite direction, so clockwise, we would get a negative or CBA sequence. Where if VAN is VP angle 0 degrees, then VBN would be VP angle positive 120 degrees, and VCN would be VP angle positive 240 degrees. In this class, we will deal only with positive phase sequence systems, okay? A negative phase sequence system does not change any of the math that we're going to do whatsoever, except it will change the sign on the angle. So it is, in my opinion, entirely redundant to spend a significant amount of time talking about a negative phase sequence system when it behaves identically to a positive phase sequence system, except that, again, the sign on the angle is changed. That's literally the only difference, and it is due entirely to the change in rotational direction of the rotor. All right. So before we get on to our variations here, are there any questions? All right, so this is the part where I would argue things tend to get a little bit more confusing, okay? So in a three-phase system, there are multiple ways that we can connect our sources and our loads. And so what we're going to do pretty much for the rest of this class is talk about the different ways that sources and loads can be connected to each other and identify specific quantities of interest. So the first one that we are going to talk about is what is called the Y-connected source. You may see it as WYE, or you may see it as the letter Y in texts. So I'm going to say that this terminal is the A terminal, then below that is B, way down here at the bottom is C. And so that means that this voltage will be voltage VAN, because it's the potential difference between the A terminal of our source and the N terminal of our source. I can similarly say that this voltage source here is providing a voltage VBN measured between the B terminal of our source and the N terminal of our source. And this voltage is VCN measured between the C terminal and the N terminal. Okay. So this is one way to draw a Y connect the source, and it's actually my least preferred way. What I prefer, because it's easier for me to draw and to look at, would be something like this. So this guy would be VAN, this guy would be VBN, this guy would be VCN, like so. So we still have all of our voltages measured between the A terminal and the neutral, B terminal and neutral terminal, C terminal and neutral terminal, respectively. But to me, the drawing on the right looks a little bit cleaner. I don't have any preference whatsoever on which ones you choose to employ. And if I'm being entirely honest, most textbooks typically go with the Y-shaped configuration. But I personally find that the box or window pane shape configuration is easier for me to understand what's going on. All right, so I would like to now introduce the concept of phase voltages. Okay, so a phase voltage is the voltage drop over one phase of a source or load. So for our Y-connected source, our phase voltages are simply the voltages VAN, VBN, and VCN. Next, I'd like to introduce the concept of a line voltage. So line voltages are voltage drops between transmission line terminals of a source or load. So these are not the same as our phase voltages for this configuration. So let me explain what line voltage is. This voltage between transmission line terminal A and transmission line terminal B is a line voltage because terminal A is associated with the positive polarity, that's the first subscript. Terminal B is associated with a negative polarity, so that's the second subscript. So VAB is a line voltage. Similarly, we can have VAB here as well. VBC is another line voltage. And finally, VCA is our third line voltage for this system. So before I move on from here and start talking about currents in our three-phase systems, is there any questions or confusion regarding the difference between a line voltage and a phase voltage? All right. Now I would like to talk about phase currents. A phase current is simply the current flowing through one phase of a source or load. So I'll do these in red. I choose to express my currents in such a way that they are flowing from the location of the highest potential to the lowest potential. So what I mean by that is that this current, ICA, will flow through the positive polarity terminal of that voltage source VCN and flow into the neutral terminal. Similarly, I will have a phase current IAN like so, flowing from terminal A towards terminal, and I will have phase current IBN. I can draw all of these on my right-hand graph. IAN, IBN, ICN, like so. Now, write those down. There is a quantity called a line current as well. But we can't talk about a line current until we are dealing with a whole closed system, because the line currents are simply the currents that are flowing through the transmission line, which connects the source to the load. So without those effectively without the other 2/3 of our three-phase system, the line currents do not exist. So we're going to kick our next lecture off analyzing a full system, and that's where I will fully introduce the concept of a line current. So before I move on to the next source configuration, are there any questions? All right. So we're now going to talk about delta connected sources. So here are our three transmission line terminals. I want you to notice that a delta connected source have a neutral conductor, okay? Literally cannot happen. So we will have a voltage VAB measured between the A and B terminals of our. We will have a voltage VBC measured between the B and C terminals of our system. And we will have a voltage VCA measured between the C and A terminals of our system. I can redraw this in a what I believe to be more pleasing view, I guess. As follows. A, B, and C, giving us a voltage of VAB, VBC, and VCA. So these are the two different ways that you might see a delta connected source drawn. So I'm going to attempt to make you guys actually participate here. Who can tell me, based on our drawings, what the phase voltages for this system are?
Would there not be any since there's no neutral terminal?
So if we go back to definition of a phase voltage, it is the voltage drop over one phase of a source or load. So I would argue that the voltage drop over our A phase is the voltage VAB. The voltage drop over our B phase is VBC, and the voltage drop over our C phase is VCA. So the fundamental definition of a phase voltage has nothing to do with the presence or exclusion of a neutral conductor. Our phase voltages for a source are always just going to be the voltage drop over the source. It doesn't matter whether it's in a Y configuration or a delta configuration. Does that make sense?
Yes, so it's just whatever the voltage is on the source or
Pretty
the
much.
drop across the source. Okay.
Exactly right. Now here's where things can get confusing, right? So if we go based on our definition of a line voltage, meaning it is a voltage measured between the transmission line terminals, we would have a voltage VAB, like so. We could have a voltage VBC, like so. And we could have a voltage VCA, like so. So for this delta connected source, our line voltages and our phase voltages represent the exact same quantity. So for the delta configured source, the line voltages and the phase voltages are identical, okay? But for the Y connected source, they are not. And I bet you can now see how some of this crap starts to get a bit confusing. For our phase currents, these are representative of the currents flowing through one phase of our source or load. So that would be this current, IAB, this current, IBC, and this current, ICA, or like so. So those are the quantities of interest for a delta connected source. Any questions before we move on to our load connection possibilities? All right. So the first load connection that I would like to talk about is the Y connected load. So previously, anytime I was dealing with a source, and this is the convention that I use in this class, I have lowercase letters. And anytime I'm going to deal with a load, I use uppercase letters, okay? So this would be terminal capital A. Then I'll have capital B, etc. But I need to draw stuff first. So I'm going to call this impedance ZYA, this impedance ZYB, and this impedance ZYC. I can draw this guy in the kind of window pane or rectangular looking format that I did the other one. Like so. And now we will identify our phase voltages. So our phase voltage is the voltage drop over one phase of our source or load. So in this case, we're obviously looking at load voltages. So I would consider this voltage measured between the A terminal and the N terminal to be one phase voltage. This voltage measured between the B terminal and the N terminal to be a phase voltage. And this voltage measured between the C terminal and the N terminal, VCN, to be a phase voltage. So our phase voltages here are literally just the voltage drop over each of these impedances. And I can write them VAN, VBN, and VCN, like so. Our line voltages. Annabelle, care to take a crack at these?
Would it be VAB and VBC?
And also
and VCA?
Yep. Absolutely correct. VAB, VBC, VCA. our phase currents are effectively just going to be the currents flowing through each of our impedances. So IAN, IBN, and ICN, like so, all represent phase currents. And I can draw them over here. So all right. So any question on the Y connected load? Effectively, all of its quantities are the exact same thing as the quantities that we saw for the Y connected source, except that they use capital letters. Otherwise, they are perfectly identical. And we'll see the same thing for our last potential configuration, which is the delta connected load. So that's our triangular or visibly delta way to look at it. And then we could also do this guy here. Where this is A, B, and C. This is the delta A, C delta B, and C delta C. So our phase voltages in this case will just be the voltage drop over one phase of each load, or effectively just explicitly the voltage drop over the impedance, right? So VAB VBC and VCA are our phase voltages. Our line voltages are VAB, VBC, and VCA. Our line voltages again represent the same thing as our phase voltages. So anytime we have a delta connection, that should be true. And lastly, we have our phase currents, which are the currents flowing through our impedances. So that would be IAB, IBC, and ICA. All right, so based on these different possible configurations, we actually only have effectively 4 different circuits that we need to be able to analyze. The YY circuit, so a Y connected source connected to a Y connected load, which is what we are going to begin our analysis on with Thursday. Then we could have a Y connected source and a delta connected load. We could then have a delta connected source and a Y connected load, and a delta connected source and a delta connected load. So these are the 4 different permutations that we're going to have to be able to analyze. Really, as you'll see during Thursday's lecture, our YY system, where we have a Y connected source and a Y connected load, is by far the easiest to analyze. We'll talk about exactly why that is on Thursday. And what we're going to do towards the end of Thursday is effectively learn conversion techniques so that we can make a delta connected source look like a Y connected source and a delta connected load look like a Y connected load, so that we can apply the easiest, we can make any 3-phase system look like the easiest possible system to analyze, so that we don't have to go through worrying about 4 different ways to analyze these circuits. So that's all that I have prepared for today. So if you have any questions, I'd be happy to stick around for a few minutes to answer them. And if not, I will see you guys on Thursday. All right, there don't appear to be any questions, so I'll catch you guys at the next class meeting.